Boyle's law. In the year 1662, Robert Boyle stated that at constant temperature, the volume of a fixed mass of a gas decreased by half when the pressure on it was doubled, and it became 4 times its original volume when its pressure was decreased by 1/4. He described this behavior in the form of a law known as Boyle's law. Boyle's law. The volume of a given mass of a dry gas is inversely proportional to its pressure at constant temperature. Mathematical expression of Boyle's law. Suppose a gas occupies a volume V1 when its pressure is P1, then V1 is inversely proportional to P1, or V1 is equal to K upon P1, or P1 V1 is equal to K, which is equal to a constant. If V2 is the volume occupied when the pressure is P2 at the same temperature, then V2 is inversely proportional to P2, or V2 is equal to K upon P2, or P2 V2 is equal to K is equal to constant. Therefore, P1 V1 is equal to P2 V2 is equal to K at constant temperature. This is called Boyle's law equation. Boyle's law may also be stated as the product of the volume and pressure of a given mass of a dry gas at a constant temperature is constant. Graphical representation of Boyle's law. The law can be verified by plotting a graph. First, V versus 1 upon P. Second, V versus P. Third, PV versus P. First, V versus 1 upon P. A straight line passing through the origin is obtained, as seen in the figure. Second, V versus P. A hyperbolic curve in the first quadrant is obtained, as seen in the figure. Note, the term isotherm, meaning at constant temperature, is used to describe these plots. Third, PV versus P. A straight line is obtained parallel to the pressure axis, as seen in the figure.
In 1787, French physicist Jacques-Charles investigated the effect of change of temperature on the volume of a fixed amount of gas at constant pressure. He stated that the volume of a confined gas is directly proportional to its absolute temperature, provided its pressure remains constant. That means V is proportional to T, or V is equal to kT, where V is the volume of the gas, T is the temperature of the gas in kelvins, K is a constant, and the pressure and amount of gas are held constant. Graphical representation. Consider an enclosed chamber with a piston on it and a water bath to heat the chamber, including an electric heating source. When the air inside the chamber is heated with a heating source via water, the temperature of the air increases. This momentary increases the pressure inside the chamber. Now, the molecules of the air exert more force in the outwards direction on the resting piston, and the air inside the chamber expands. For a given amount ideal gas, V1, T1, and V2, T2, are the volumes and temperatures of the initial and final conditions at constant pressure. So, from Charles' law, V1 by T1 equal to V2 by T2.
Gay-Lussac's law of pressures. Consider a constant mass of a known gas at constant volume. When the temperature is increased, the pressure on the gas increases relatively. Thus, pressure is proportional to temperature. Stated mathematically, P is proportional to T, or P is equal to kT, where K is a constant. For a certain mass of a gas at a fixed volume, P1 by T1 is equal to K, and for the same mass of gas at the same volume, P2 by T2 is equal to K. These equations lead to the conclusion P1 by T1 is equal to P2 by T2.
gas law, which is sometimes expressed as PV, pressure volume, equals nRT, which is the number of moles times the gas constant times the temperature. And now the temperature is measured in Kelvin. And so at 0 Kelvin, the molecules aren't moving. How cold is that? That would be around negative 273 degrees Celsius. Have we achieved that in the universe? Well, close. In the Boomerang Nebula, it's around 1 or 2 Kelvin. And in laboratories, we've gotten within fractions of degree Kelvin by bombarding the matter with lasers on all sides to stop molecular motion. It starts to form a new state of matter. But with a gas, we have these molecules that are bouncing around, and there are a number of macroscopic characteristics that we can measure in the laboratory. So we've got the pressure exerted by the molecules on the container. We'll use P to represent that. We've got volume, that's going to be the area in which the gas is contained. We've got the amount, and we'll measure that in N, which is going to be the moles of the material. And then finally, we've got temperature. Temperature is going to be in Kelvin. And so we can think of this like a scale. And so you can think of it as people sitting on a teeter-totter. And so what would happen if we increase the pressure? Well, to keep it balanced, we'd have to decrease the volume. What happens if we increase the pressure? If we're changing the temperature, then we'd have to increase the temperature. Now, it doesn't work exactly like this. We have a constant called the gas constant that makes it all equal. And in chemistry, you'd have to do a lot of calculations for this. But in physics, you just have to know qualitatively what's 173. And so we're going to use a PHET simulation to do this. R is the gas constant, but what's neat about the simulation is you could measure the volume. That's how big the container is. The temperature, we've got a thermometer. We've got a pressure gauge on the side, and then finally we have N, which is going to be the number of molecules that we're adding. And so here's the relationship, PV equals nRT. And so let's look at pressure and volume and the relationship between those two. So what happens as we increase pressure, if we're keeping the other ones constant? Think of that teeter-totter again. If you increase the pressure, we'd have to decrease the volume. And this was studied by scientists. It's known as Boyles' law, but let's use a PHET simulation to measure it. So what we're going to do is try to keep the temperature constant, and we're going to look at the pressure, and then the volume is going to be how big this container is. So what I did is I decreased the volume. Now what happened, the temperature went up right away, but we're using ice to cool that back down to where it was. And so what happened is as I decreased that volume, what happened to the pressure gauge? Now the temperature's back to where it was. You see we saw a great increase in that pressure. Now I'm going to increase the volume. Watch what happens to the pressure as I increase that volume, we're going to see a decrease in that pressure. And so there's a relationship between the pressure and the volume. If we were to, keeping the temperature exactly the same, if we were to graph it, it would look like this. And so what we have is if we increase the volume, so I'm going in this direction, what happened to our pressure? Our pressure decreases. What happens as we decrease the volume? What happens to our pressure? Our pressure is going to increase. Now, why do we have a number of different lines here? Each of these are going to represent different temperatures of the gas, as long as we keep those temperatures constant. Now let's look at the relationship between the volume and temperature. So if we keep all the other ones the same, so what's going to happen? Well, imagine they're on either sides of the teeter-totter. If I keep the pressure and the number of molecules the same, as I heat it up, as I increase the temperature, we're going to increase the volume to keep it balanced. And so why is that? Increasing the temperature increases the average kinetic energy of the molecules. There's moving around faster. If we keep the pressure the same, so that change in momentum as they collide with the container, as we increase temperature, volume goes up. As we decrease temperature, watch what's happening, the volume is going down. Now this is a direct relationship. So if we were to graph this, that's that absolute value calculation I showed you just a second ago. As we increase temperature, bigger volume. Decrease temperature, lower volume. If we play this out and extrapolate it, absolute zero. And so did you learn to extrapolate from a volume versus temperature graph to figure out absolute zero? Do you understand how you could design an experiment to play around with these using the PHET simulation? Remember, you want to keep some of them constant and then just change one at a time. And then finally, could you analyze the relationship between pressure and volume? So we're going to get these curves. Each of those represents a different temperature, and I hope that was helpful.